Issues are not the most important, they are still important. So today I'll see how to compute page rank very fast. I'll start with things which are classically well known and very simple, and then I'll give you one proof of how you can compute page rank much faster than you would expect in a quite a surprising setting. And then I'll give you another algorithm, but not quite give a full proof for personalized page rank. Yeah. Everything that I talked about yesterday was implemented. Things that I'm going to talk about today are more oriented towards research. Yeah. So for page rank, there's a classic way of computing page rank. It's called power iteration. And it's going to be, the proof is very simple, but I want to run through it anyway. And then there's another way of computing page rank, which is called Monte Carlo. And again, it's very simple, but I'll run through this anyway. Power iteration is simple enough that we can do the full proof. For Monte Carlo, we need some tail bounds, which I don't want to go through. So I'm going to just tell you roughly what it is. Okay? So the way to compute page rank using power iteration is to initially do it in stages. So initially set pi 0 v equals 1 over n for every node v. So you start it out as being 1 over n. And then you repeatedly run an iterative step. You say pi k of v equals alpha over n plus summation over w comma v in E of pi k w pi k minus 1 w divided by out degree of w, okay, and the whole thing times 1 minus alpha. Okay. So it's basic power iteration. You use the k minus 1th iterate to compute the kth iterate. Yes, k minus 1, yes. So you're using the values from the k minus 1th iteration to compute the kth iteration. And so you start with 0 and you keep going, and after some time you're going to converge. And the basic proof is just to say that this is a contractive map. And the way you would show it is you would say, if you look at the true page rank as defined last time, and you look at this difference and take the absolute value, then this term just washes out. Out here you get pi k minus 1 w over, you get pi w minus pi k minus 1 w. But because of triangle inequality and we're taking absolute values, this equal to becomes a less than equal to. The 1 minus alpha remains, and you get summation of w comma v in E of the absolute value of pi w minus pi k minus 1 w. And I know that there was it was hard to view it from the back, so please do interrupt me early if it's hard to see. Divided by the out degree of w. Okay. And so, but now we're going to sum this over all v and sum this side over all v. When we sum this over all v, what we're going to get on the left hand side is just going to be what I'll call delta, let me call it error in the kth step. The total error in the kth step when I sum this over all v, how far is your kth iterate from where you would need it to be. This would be less than equal to 1 minus alpha. Okay. And when we sum this over all v, and we are already summing over all w, all edges here, we are really summing over everything. So this node w is going to be in the summation exactly out degree time. So this out degree is going to cancel out. And so because the out degree cancels out, you get error in the kth step is less than equal to 1 minus alpha times the error in the k minus 1th step. Okay. The initial error was 0. Sorry, the initial error was at most 2. And that's sort of easy to verify, okay, because you set everything to 1 over n. So you could, the total underestimate you could have is 1, the total overestimate you could have is 1. And so this tells you that error of k is less than equal to 1 minus alpha to the power k times 2. Now, you would ultimately like the error to be something like epsilon times epsilon over n. Okay? The average page rank is 1 over n. So, ultimately you would like the error to be something like epsilon over n. Does that make sense? So, which means that after something like log n times log of 1 over epsilon iterations, you get good convergence. Okay? And again, the exact number of iterations you need of this power iteration method depends on the exact bounds that you want. If you want a total, if you just want a total variation bound, you want the total distance to be epsilon, then you'll be done in constant iterations. Okay? So, I'm going to ignore this dependence on epsilon because normally we don't want epsilon to be that small. I'm going to just focus on the log n part. Okay? So, if you think about it roughly, after roughly log n iterations of power iteration, you are done. In practice, you would do 10 iterations of power iteration and everything converges beautifully. Okay? There's also a lot of slack here because I use triangle inequality. So, in practice, it converges much faster. Yes? Oh, there's also a 1 over alpha, sorry. Sorry. Is log of n over epsilon. I just switched the epsilon and the alpha in my mind. Is log of n over epsilon times log of 1 over alpha. Okay? And the thing that, or is it divided by log of 1 over alpha? Okay. Sorry. Yeah. Yeah. I'm just not used to sort of thinking of epsilon and alpha carefully, because at least in this domain, alpha is typically, like I said, some constant, and you typically want a small epsilon. Okay. So, if you have to focus on something, please focus on something like log of n or log of n over epsilon, because that's the term that's the most important. Okay?
I think that's where the log n came from.
So, because ultimately you want the total error to be like epsilon over n. Because the total error is epsilon over n, then you can be pretty sure that because the average, you know for sure that for any v, pi of v is greater than equal to alpha over n. Okay? Because that's just the reset probability, the teleport probability. Because you are sure of that, the accuracy that you really want is something like epsilon over n. Just to make sure, if your total variational distance is at most epsilon over n, then nobody is more than epsilon over n away. And so, you know, you have a good approximation to the page rank of every node. Okay. So, once again, I think the important term to keep in mind is roughly this log n. It's good to know that the remaining, there are no other ugly constants hiding here, but the log n is really the important term. And once again, normally when you have 1 over epsilon, you're normally worried about epsilon. But in this case, epsilon and alpha are going to be some constants. They're not going to be like tending to 0. Okay. The second approach is Monte Carlo. And Monte Carlo is basically what you would expect. You just simulate So, you just simulate the page rank random walk, and the page rank random walk is very simple. You start at a random, uniformly random node. Okay. So, this is what I would call a short random walk. Okay. So, a short random walk starts at a uniformly chosen random node V. Okay. With probability 1 minus alpha, it proceeds to another node W, a uniformly chosen out neighbor of V. With probability alpha, it stops. Okay? And so that's just a short random walk. So it'll keep going. Maybe from W, it'll go to W prime. Maybe it'll stop at W prime. This W prime is what you return as a sample. Wherever the random walk stops is the node that you return as a sample, not the entire path of the walk, but just the final node. Okay? And so this takes roughly 1 over alpha steps. Okay? And 1 over alpha steps, you get a uniformly random sample from the PageRank stationary distribution. And so again, you want accuracy something like, so it takes 1 over alpha steps or one short random walk to get one sample, which is uniformly, which is from the stationary distribution. You need something like n over epsilon squared samples. Okay. And so to get this accuracy of, because once you have these many samples, you get enough confidence that you have the right answer. Okay. Sorry, maybe you need n log n over alpha epsilon squared samples to make sure that you have enough confidence. Okay. And maybe there's an alpha inside the log, but I'm going to ignore that. Okay. And so I'm going to think of this as roughly R n log n. Random walks. Okay. So this R, I can think of this as R times n over alpha random walks, and this R, again, the dominant term here is going to be log n. It's going to be log n over epsilon squared, but like I said, epsilon is some constant. It's not tending to 0. Okay. So the log n comes from tail bounds. So you have n nodes. For each of these n nodes, you want a sharp concentration. So you apply some, and you're getting uniformly random samples. So you apply some standard probabilistic bound, and what falls out is something like log n over alpha. So again, the log n is not important, it's just part of R. So you can think of Monte Carlo as you're doing roughly R times n over alpha random walks. Okay? Where R is some small number, think of it as log n. This R is comparable to what we had in power iteration. In power iteration, we had R times m time. Okay? So n is the number of nodes, m is the number of edges. Is it clear why the running time of power iteration was R times n? Is because you're doing these two R's, even though they're slightly different things in terms of log n. I'm going to think of them as roughly being the same. It's m because each power iteration takes m steps. Because each power iteration, if you remember, was just updating the page, taking the previous page rank values, computing the new ones, and that you can do by one-step propagation along all the edges, and that takes m steps. So let's just keep these two numbers in mind: Rm for power iteration and Rn over alpha for Monte Carlo. Okay. And let's see if there are any surprising computational results here. So for example, so by the way, the numbers remain the same if you want personalized page rank. When you personalize page rank, you can also compute that using Monte Carlo or using power iteration, okay. And the analyses remain about the same. Okay. R is log n times some other junk in both here. So in both cases, if you want strong guarantees, R is log n times the other junk. The other junk is very different from power, looks very different from in power iteration in Monte Carlo if you are used to general stochastic systems analysis, because you initially your tendency is you're thinking of epsilon going to 0, and so 1 over epsilon squared and at 1 over epsilon inside the log looks very different. But in these particular cases, you typically would have like alpha equal to 0.3 or 0.2. You might have epsilon equal to 0.1. So these numbers are not They're far apart, but they're not that hugely far apart. In fact, I often run these algorithms epsilon alpha equal to 0.2 and epsilon equal to 0.5. So actually allowing more deviation than the average, because they're typically interested in things which are in PageRank which is well above average. So typically interested in like deviations of up to 1. You can tolerate deviations more than 1 over n or more than 2 over n. So with this background, I want to quickly show you a couple of results. One of them we'll see in detail, one of them we'll see a vignette of how you can get, it might seem like some of these algorithms might sound like they're going to be very inefficient. I'm going to just show you how you can sometimes run them incredibly efficiently. So we're going to look at 2 computational questions. No. Sorry, you mean in Monte Carlo or in power iteration? No, it doesn't matter what the odd degree is for Monte Carlo. So the Monte Carlo is actually very robust. There's no, because in doing this uniform sample, it doesn't matter what the out degree of a node is. You can sample. So let's assume the node is given. So we have to get in the details, but let's assume that a node is a node's adjacency list is given to you in an array. Okay. Then all you have to do is to pick a uniformly random node from this array, and that's a very efficient operation. Now you're right that formally it might seem like picking if you have an array of size, let's say the out degree is d, formally it might seem like picking a uniformly random element out of this is going to be very expensive. But in fact, no matter what d is, you can pick a uniformly random element in actually constant time. And this might sound like a funny optimization, but in fact Twitter actually did this optimization to just not even to take random samples in constant time. Was that your worry that? Yeah. So you can do a small amount of pre-processing, which is the same as just, in any case you have to read them into memory. So of course to do Monte Carlo, I guess you could say that Monte Carlo takes time at least m, because you have to read the whole thing into memory. So I guess I'm ignoring the time it takes you to read the network into memory. But when you're reading the network into memory, you can pre-process this, so you can do constant samples, you can do random samples in constant time. So the first question is fast incremental PageRank, okay? And this is sort of related to the question that just got asked. So in something like Twitter, updates to the social graph are made in real time. Okay? So a lot of you must have seen PageRank in the context of something like web search. So what happens in web search is that you go and get a crawl. You do crawl, and then you get an entire copy, new copy of the web. And then you can run PageRank on that entire copy of the web from scratch. In social graph, what's happening is that these updates are happening in real time, and you know these updates as they're arriving. It's not like you have to go and crawl the web to find out how the web changed, right? So you have these real-time updates, and in a place like Twitter, there are these trending things that happen. So some things become suddenly very important. Okay? So you could imagine that it's important to capture these trending events. So as soon as an edge arrives, you want to update the PageRank of every node. Okay? So once again, just to clarify, okay, because it might not be obvious, this is a motivation, it's a reasonable motivation, but these algorithms are not actually implemented at Twitter. Whereas the ones that I talked about yesterday, the collaborative filtering, cosine similarity, the money algorithm, those are actually all implemented and running at scale. So this is well motivated, but not actually implemented as far as I know. So our goal is to design an algorithm to update PageRank incrementally, for example, upon an edge arrival. So we're going to need some notation for this. Let's say the tth edge arrives, okay, and let ut comma vt denote the arriving edge. Okay. Let dtv denote the out degree of node v, okay, at time t. So the reason everything is prefixed with t is because these things are happening over time. And let's say pi t of v is the PageRank of node v at time t. Okay. So it's different from power iteration. In power iteration, those iterations are something that we were running. Here pi t of v is just being given to us by nature. At the t at time, a node arrives. Okay. I'm going to make a slight assumption here. Okay. And the assumption I'm going to make is that I'm going to assume that the graph is adversarial, the network is adversarial. So we're not going to assume any generative model on the network. For those of you who have seen papers on social networks or web graphs, it's quite often to assume that these networks are being generated from some model, okay? Either the power law model or the Ardor-Shenny model or the forest fire model. So I'm not going to assume that the graph comes from a model. So I'm going to assume the network is adversarial. Okay? It's arbitrary. But I'm going to assume that the edges of this network are arriving uniformly at random. Okay? So we have an arbitrary network, but its edges, what we're getting is a random permutation of its edges. Okay? And so does the distinction make sense? So can anyone guess how much time it will take as t increases, as more and more edges arrive? Can anyone guess how much time it will take to process the tth edge? I described it to somebody over tea yesterday, so anyone except that person. Sorry? Linear in t? So it's a reasonable suggestion, right? Because the tth edge arrives, your network is getting bigger and bigger, so it's reasonable to say the time to process this edge is also going to get bigger and bigger, right? I'm going to do this thing which my wife sometimes does when she goes shopping. She brings something and she says, can you guess how much it is? And she gets very upset if I guess less than what she actually paid. Can anyone, any other guesses? It's much less than that. It's actually even less than that. It goes to 0. So the time to process the tth edge actually goes to 0. So as the network is getting denser and denser, is bigger and bigger, you think the problem is getting harder and harder. But in fact, the time to process this edge is actually going to go to 0. Yeah. So it's going to be because of Monte Carlo. Yeah.
So basically, the problem is I want to move the spectrum from 0 to t, and I don't consider that perhaps it's more important to forget that.
So yeah, so I think basically you have the page rank of every node. You're maintaining the page rank of every node. Another edge arrives and you have to update the page rank. Yeah, it's a perturbation quotient. Yeah. Yeah. So which is why it's not surprising that it goes to 0. So just computing the perturbation that would happen from the t minus 1 step to the tth step. Yeah. So we're going to do this incremental page rank via Monte Carlo. Okay? And this is another reason why Monte Carlo is very robust. So you start with r equals order log n. Again, I'm going to forget that r, like I'm going to forget all the epsilons and the alphas. You start with r equals order log n random walks from every node. Okay? So remember I said that you need like, let's even forget this alpha, because I'm going to assume that alpha is also a constant. I said that you need r times n random walks total. Okay? That's like saying that you need r random walks from every node. Okay? Because each of these r n times you're starting with a uniformly random node. Starting exactly r times from every node actually gives you slightly better stochastic properties, not worse. Okay? So you start r equals order log n random walks from every node initially. At time t, you have a node arriving, and the node that arrives at time t is the node, there's an edge arriving, and the edge that arrives is ut comma vt. Okay? Now any random walk that was not passing through the node ut doesn't actually have to change, because none of its outgoing edges changed. So by a coupling argument, if you run Monte Carlo now, you would do exactly the same thing as you did before. Okay? The only place where this coupling will break down is for random walks that go through ut. Okay? And for any random walk that goes through ut, you just reroute it. Okay? And you reroute it to use the new edge ut comma vt. But again, by a coupling argument, this rerouting needs to happen with probability which is 1 over the degree of ut at time t. Does this make sense? And this degree of ut at time t is the degree of ut after the arrival. After the arrival of this edge, the dt ut edge is going out of ut. You're going to do this rerouting with probability 1 over dt ut. So that's all I'm saying there. Okay? And so the time or the number of network calls, if you store this in distributed memory for doing this rerouting, is going to be 1 over alpha. Is it clear why this is going to be 1 over alpha? Because these random walks are only 1 over alpha long. Okay? So any short random walk is only 1 over alpha long in expectation, because the reset probability is, teleport probability is 1 over alpha. So you just do this rerouting, and the claim is this faithfully maintains R random walks after arbitrary edge arrivals. Okay? So what that means is this process simulates Monte Carlo exactly. Okay? Because this mimics Monte Carlo exactly, I don't have to give you any correctness results. Okay? It's already correct because I'm doing exact Monte Carlo by a coupling argument.
What do you exactly do in the reroute?
You reroute to Vt, and then you keep going. Now, because it's resetting each time with probability 1 over, with probability alpha, it's a memoryless process. You just go to Vt and you keep going from Vt as if you were starting the random walk at Vt. And after 1 over alpha steps in average, it'll terminate, and that's it. So all we need for this is the graph and the short and the stored random walks in fast distributed memory. I'm going to tell you the running time that this entails, and I'm going to prove the running time. I think that's going to be the only proof for computation. So, like I said, I'm going to assume that the edges of the graph are chosen by an adversary, but then presented in random order. Okay? This is actually a fairly weak assumption. If you assume that the network is Ardouch-Renyi, then of course that's a stronger assumption. Ardouch-Renyi is where any two nodes have an edge between them with constant probability. Assuming that the network is a preferential attachment model, the preferential attachment model or the forest fire model or any of these standard exponential model, any of these standard models of social networks, they are actually equivalent to saying that you first generate the edges and then present them in random order. Okay? So, so there's a theorem is that the number of reroutings per arrival goes to 0. And so the only amount of work you have to do is the objective of the adversary would be to maximize the amount of time that you spend in these reroutings. Right. This is also sort of betraying my background a little bit. This is a little bit more of like a theory CS style thing. I think for this community, I think a better way of saying it would have been that the edges are arbitrary and they're just present in random order, as opposed to saying they're generated by an adversary. So the main theorem that the main result that I'm going to prove this a little bit later, is that for the tth arrival, the number of reroutings is order of nr divided by alpha t. And because t is the number of edges, not the number of nodes, as t becomes large, as the density of the graph increases, this number goes to 0. Okay? And so just summing over all t, the total time over m arrivals is going to be n times r times log n. Why do I have an extra alpha? Log n over alpha squared. I don't know why I have an extra alpha. So the log n comes from integrating 1 over t. Okay. Log n and log m are the same because you assume that m is at most n squared. Okay. So someone said, why is it log n and not log m, where m edges are going to arrive? And so the nice thing is this is comparable to doing power iteration on Monte Carlo just once. So as your edges are arriving, you are maintaining you're doing exact Monte Carlo, right? It's not even an approximation. And the running time for this entire arrival, for these entire m edges, is actually comparable to doing power iteration on Monte Carlo just once. Okay. So for example, Monte Carlo takes nr over alpha time, okay, and we are taking nr log n over alpha squared time. Oh, sorry, I know why there's an extra 1 over alpha, sorry. The extra 1 over alpha is the number of reroutings, but each rerouting takes you 1 over alpha steps, because the random walk is 1 over alpha long. So one Monte Carlo takes nr over alpha if you are given the graph, and here the entire thing is taking you nr log n over alpha squared time. So you're only paying an extra log n over alpha compared to just doing Monte Carlo once, and you're getting the entire history. For power iteration, it's actually even better. Power iteration takes time mr over alpha. Okay. And so you have n log n over alpha versus m. Okay. And that n log n over alpha versus m might actually be smaller than, n log n over alpha might actually be smaller depending on how dense your graph ultimately ends up being. So might actually doing Monte Carlo all the way through might actually cost you less than doing power iteration once. So I just want to do this quick proof of just this one idea. The tth arrival for the number of reroutings for the tth arrival is order nr over alpha t. And I might ignore things like 1 over alpha and so on. So does the basic idea seem clear, right? Is it obvious that, yeah?
It's just, you want this to be, the sample be accurate for each of the time. Shouldn't there be still some factor coming in? Because, for every given time t,
Yeah.
it's a
Yeah.
kind of thing at the bounds.
Yeah.
But if you want it to be,
Yeah.
the accuracy
Yeah.
of all of them jointly, there should still be some more coming in. Depends what you're
Yeah, yeah. So I think, yeah, that's a very interesting and subtle point. So I think the errors in different steps are not independent. So whatever error guarantee Monte Carlo provides, you get that error guarantee at any given t. But the errors that you have in Monte Carlo, they're not independent at different t. Is that, so you get coupled errors. So if you wanted,
Yeah, so the question is at the end, do you want to guarantee that for every time step you have
Yeah.
the max error is guaranteed, then I think you need more samples. If you
Yeah.
just want one particular
Yeah.
given time step, then
yeah. So for example, if you wanted to make sure that you always have, that you have correct bounds at every time step, then you have to add another log n. Because the way the Monte Carlo bounds are calculated, actually no, I don't think you have to, sorry, I take that back. So the way the Monte Carlo bounds are calculated, the reason you have this log n is because you want to make sure that none of the nodes is very far away from its page rank. If you want to apply this probabilistic bound over n times m steps, then this becomes log of n times m. So maybe instead of having r equals log of nm, if I could just change r equal to log of, instead of having r equal to log n, if I change my r to be log of nm, then I'll get bounds across all time. So that would be like an extra constant 3, factor 3 or not. But it's definitely true that right now, the bound that I get, the errors are not independent across time. I was asked to repeat the question, which I forgot. But the question, because not everyone can hear the question, but the question was roughly, how do the errors relate to each other over time? Are we getting a bound across all time or for any one given time? I found this result very surprising. And so this was joint work with my student Bahman Bahmani and Abdur Chaudhary, who was the chief scientist at Twitter. And this is the same paper where we did the analysis of various recommendation systems, the empirical analysis that I showed last time, saying that money is better. So it's almost like two separate things, like an empirical result and a theory result. And I thought that this would be the way we would implement PageRank, but we ended up just doing it directly as opposed to doing it incrementally. So let's focus on the tth arrival. So during the tth arrival, the number of reroutings is going to be And so this is so the total number of random walks that short random walks that we did is n times r. Okay. So this is the total number of short random walks that we did. Okay. Maybe there's an alpha here. Okay. The total length of these random walks is nr over alpha. The number of these random walks that pass through ut is going to be pi t ut times nr over alpha in expectation. Okay. And the reason is because the Monte Carlo is the same as the stationary distribution of the page rank, right? So the number of random walks that we expect will go through ut is going to be nr over alpha times the page rank of ut at time t. Does this make sense? So the total number of random walks that go through ut. Each of them is going to get rerouted with probability 1 over dt ut. So this is the expected number of reroutings that are going to happen. Okay. So goes to ut. So this is sort of any walk that goes to ut is going to get rerouted with the probability.
Choice of VT, UT, VT.
Yeah. So pi t is the page rank of ut in the tth step, right? So does this, right? So this is basically the same thing that we had before. This is the probability that's rerouted again. Now this expectation is over the choice of the edge ut comma vt. Does that make sense? Now, but at this time, the number of edges in the network is exactly t. But the assumption that we made is that these edges are presented to us in random order. So the probability that the edge ut vt is the one that's presented to us at time t is exactly 1 over t. To 1 over t. Okay. And therefore, the probability of seeing a node ut as the first node is exactly equal to dt of ut. The probability that ut equal to u for any node u is going to be exactly dt of u. Okay. And so this is where the random order assumption comes out. Okay. So because this expectation is over the choice of ut comma vt, I can sum this over all u and multiply it over dt over t. Okay. So I think this is the main proof step. Okay. The probability that ut equal to u is exactly the degree of u divided by t. Okay. And intuitively that makes sense because I assume that edges are arriving uniformly at random. So whatever happened, you look at the graph at the end of time t, and then you say, well, I don't really know which edge is the most recent one that arrived. Any of them could have been the most recent one that arrived. Okay. And so the probability that I saw the node u is going to be exactly equal to its degree divided by t. But if I do that, then I just multiply this with the probability of seeing ut, which is dt of u over t. The degree cancels out, and I have to sum this over all u. So this probability is equal to summation over all u of pi t u times nr over alpha times dtu times dtu over t. And this dtu over t is the probability that I saw u in the very last step. And so the dt cancels out nicely. The 1 over t is the 1 over t that you see there. The nr over alpha is the nr over alpha that you see there. And the summation of pi tu is 1 by definition, because pi tu is the page rank, so the Hessian distribution of some random walk. So basically, what this says is that because you can use Monte Carlo for either personalized page rank or global page rank, because this time is going to 0, even if you are maintaining the personalized page rank for every node, even if you're maintaining not one page rank vector, but n page rank vectors, one personalized to every node, you could still be able to update them reasonably fast in real time as edges arrive. So, no, because it's just expectation, so I don't need concentration. Yeah. The result is an expectation. Yeah. So you're saying, could we also get concentration? Oh, sorry, expectation, sorry. Yeah. 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 Expected number of readouts, yeah, thank you. Yeah. So this is sort of one computational result. The next computational result is, so by the way, sorry, again to take one more second, not to belabor the issue. The algorithm that we saw last time, money, was personalized page rank, right? And so because this incremental page rank is very efficient, you could imagine doing money from every node, maintaining the money relevances from every node, and updating them in real time as edges arrive. So the next thing is personalized page rank. Right? And so somehow I feel like network-based personalized search is not yet very mature. So if you go to any websites, so for example, even if you go to Twitter or Google or Facebook and you do a search, you'll find that this search is often personalized to your interests, but it's not really personalized to your network. And I think one of the reasons is there's a missing technical piece here, and the missing technical piece is efficient algorithms for personalized page rank queries. Okay. And so what's a personalized page rank query? Given a source S in a target T, estimate the personalized page rank of T for S with high accuracy if it's greater than delta. Okay. So there's some number, some threshold delta that you want. Okay. You're given some result, and you want to find if the personalized page rank of T is starting from S has high accuracy. Okay. It might seem a bit abstract, so I'm going to give an example. These examples are dangerous because companies keep improving their search. So it's possible these searches have improved by now. Sorry, I checked before I started the talk. It was working before the talk. Maybe it's going to work again. Okay, maybe I should stop spending more time. So if I have time at the end or maybe at the beginning of the next lecture, I'll give you an example of why I think network-based personalized search is not very mature. But for now, this is a technical problem we want to solve. You're given a source S, you're given a target T. You want to do personalized page rank from S. What that means is when you do teleport, you teleport always back to S. And you want to find in this personalized page rank, is the page rank of T, the target T, going to be more than delta, where delta is some threshold that you have. And delta is typically going to be very small. So you can think of delta as being like 2 over n, 3 over n, 4 over n. Because the average page rank is going to be 1 over n, so delta equal to 4 over n is 4 times more than average. S and T are 2 nodes in the graph. Yes. Yeah. And so just to remind you of personalized page rank again, it's the same as before. Given a consumer C, you perform a random walk on the follow graph or any graph. And the walk is at node V, then the walk jumps back to node C with probability alpha, as opposed to a uniformly random node, and follows a random edge with probability 1 minus alpha. Yeah. So here's some existing methods for personalized page rank queries. Okay. So Monte Carlo uses time 1 over delta.
The graphs are different. I mean, the one is the social graph or whatever
Yeah.
person, and the other is a web graph.
So it depends. So for example, even on the social graph, the personalized search is not very good. So even a social graph, if I search for someone, we'll find that these results are not very good. Let me see, maybe my network is working. Are you on Twitter?
No.
Okay.
No, don't query for me. You don't know what you're going to find.
So I search for algorithms. If the results show up, then I'll show them to you. So ideally, at least when I search for algorithms, and given that I work in algorithms, I would find the results. I would expect the results to be very tailored towards my network, and my network is heavily algorithms of the type that we are seeing here. I don't do deep learning or machine learning or anything. So you would assume that if it's doing any kind of personalization based on my network, it's going to show me results from complexity theory, from algorithms, from networks, from page rank, but not from deep learning and machine learning. And you'll see all my results are going to be deep learning. Again, it's dangerous to make these assumptions, this claim, because I haven't actually seen the results. So who knows what's going to come out. But if it comes out, I'll show you. Then again, even for web search, exactly the same thing applies. So when you do this personalization, I'm showing this personalization as if you're jumping back to a specific node C. But personalized page rank works equally well if you're jumping back to a set of nodes S, uniformly at random. So the way you would do personalized page rank on the web is you would look at those web pages which I've bookmarked, or those web pages that I often go to. Say like the top 100 web pages that I go to, and you could jump back to those top 100 web pages, and then I would get something personalized to me. So even though it's stated in the language of social networks, it also applies to web search. And then there are lots of other situations, like for example, citation ranking. So if I go to say any citation search engine, and I search, say on scholar.google.com, and if I am an author myself, I should personalize to the set of papers that I wrote in the citation network. You can imagine the citation network, and imagine doing a personalized page rank where the seed set is the set of papers that I wrote. And you can see that makes a, we used to have a demo where you could see that makes a big difference in the quality of results that you get back. Sorry. So the question is, what's the stationary distribution? So what happens is that you're going to do a walk. You're doing this random walk. Imagine that you do this random walk not for a few steps, but imagine that you do this random walk for say 1,000,000 steps, 1,000,000,000 steps, 1,000,000,000,000 steps. If you do it for long enough, because of the randomness, this random walk will mix, which is to say it'll get into some distribution where the probability that you are in some node is not going to change from time to time. It'll change which node you are at, but not the probability of being at a node. and that probability is a stationary distribution. So if you do personalized PageRank queries, you could do them using Monte Carlo. If you want, since I said I'm looking for threshold delta, and again think of delta as being 1 over n or 2 over n, you can use Monte Carlo. It will take time roughly 1 over delta, ignoring all the things that you need to do to get probabilistic certainty. You're never able to?
To recover the whole graph. Or have you also link? So when you have a given picture, you have also another all the link, or you have some old.
Oh, so the question is, do you have the whole graph or just the?
Yeah. How you? So in reality, right?
You have the whole graph.
You have the whole graph.
So in Twitter, for example, in many situations you have the whole graph. In Twitter, you definitely would have the whole graph. The whole graph will fit into some so we think of these graphs as being big, but let's think of Facebook. Facebook will have 1 billion nodes, let's say 2 billion nodes, and let's say 500 billion edges. That's 500 billion edges is going to fit on a 2 terabyte machine in memory, and that's not that much.
No, but okay, it's more for application of point of view. Of course, if you have visited Twitter,
Yeah.
you have the whole graph.
Yeah.
But assume that you're an advertiser and you want to do targeting advertising.
Yeah.
On the graph. In
Yeah.
this case, you don't have the whole information. You have feedback from some nodes.
Oh yes, but the people who are doing the targeting will have the whole information. So you could imagine that the targeting is being done not by the advertiser, but by Twitter or Google or Facebook.
So you pay them basically.
Yeah. And so the question was, well, how will someone like an advertiser or a recommender, because I said these things are applicable to advertising, how will they have access to the whole graph? And the reason these companies, the reason companies like Google and Facebook and Twitter can charge a premium for advertising is because they are the ones who control the targeting information. So the advertiser has no way of reaching these users directly. The advertiser would pay Twitter and Google for clicks, and then it's up to Twitter, Google, and Facebook to target the ad in the right way. Yeah. Yeah. So the question is, would you need to have the whole graph in memory because you're doing short random walks? No, unfortunately, yes. So in Facebook, you can reach pretty much anyone from anywhere in 4 steps. So if alpha is 0.3 or 0.2, you're pretty much going to be half the time you will end up going pretty much through the whole network. For the web graph, I think the reason the belief was that the personalized PageRank is like 1/5 or 1/6 is because the diameter is quite small. So I think I once got a copy of the web graph as it existed in 1998. So I know it's not super new, but the diameter there was like 20. So with an alpha of 0.1, you would actually essentially need to have the whole graph. Also, even though you might say that you're not expanding the whole graph, the query node could be from anywhere. So in this kind of a setting, the querying node is me, and I could be an arbitrary node. So you would have to have the whole thing sitting in memory somewhere. But these graphs are not that big, so having the graph sitting in memory is not that hard. The hard part is if you have to replicate the graph many, many times, once for each individual, that's when it becomes very hard. So Monte Carlo will take time 1 over delta. There's another method called local update, which uses time d over delta. And this local update basically does what I think you were hinting at, which is you get a node, you expand the neighborhood of that node, you propagate the PageRank values out to that node, then you expand the neighbors of that node, and you keep propagating out. I didn't do a good job of explaining that, but basically you start at a node S, and you say this is my source node S. This node is going to have a personalized PageRank of alpha, at least because that's what I give it. The remaining 1 minus alpha it has to send out. So it send out the remaining 1 minus alpha to all its nodes. And then all of these nodes will realize, oh, the alpha of this I've got to keep because that's the probability it'll reset here. The remaining I've got to send out. And so they'll send that out. But then you put them all in a priority queue, and you always send out from the one that has the highest residual right now. and that's basically local update. So local update takes time d over delta, where d equals m over n is the average degree. Yeah. So but 1 over delta is actually, so 1 over delta is very large, because you typically need delta to be something like 4 over n or 5 over n. So if you want to be able to find the top, distinguishing the top 1% nodes and the average node, you need delta over n to be around 4 over n. Yeah. And so the result that we have is that we can answer personalized PageRank queries in average time, which is O tilde of square root d over delta. And the average is over the average s and an arbitrary t. And the worst case time of square root d over delta with square root d over delta storage and pre-processing time per node. So I think this is where the storage has to be prohibitive. So it's not storing the network once is not a problem, but if you have to have O tilde square root d over delta storage and pre-processing time per node, that's when it starts to be prohibitive, because you're going to have to replicate this node, this graph tens of thousands of times. And so, so typical values with typical values of delta equal to 10 to the power minus 8 d around 100, it results in a 100-fold decrease in the amount of time it takes to do personalized PageRank, say compared to just basic Monte Carlo versus versus what we have here. And so this ends up being a big improvement. So I feel like for the first time, I feel like we are at a point where you can do these personalized PageRank queries reasonably efficiently. And so I'm not going to do the proof of this one, but the intuition is to use something like the birthday paradox. So you imagine that you do a small number of forward random walks from S. Okay. So you start walking from S, but you don't really look for nodes which have PageRank 1 over delta. You only look for nodes which have PageRank 1 over square root delta, roughly. Then you do reverse PageRank computation from T using local update. Okay. And again, this local update is basically very similar to the one that I just described, and use the number of collisions as an estimator. Okay. But again, using the birthday paradox, you need the collision probability to be small. But by birthday paradox, if you have a set of size k, if you pick two sets of size square root k, then they'll have an overlap with high probability. And so basically, we use this number of collisions as an estimator, and we need to catch a collision just before it happens. And again, I think since we already saw one proof in detail, I don't want to do this proof in detail. But basically, the result that we get is that for a uniformly random target node T, sorry, I might have said S before. For a uniformly randomly chosen target node T, the average per query running time is 1 over square root delta times d tilde plus log n. So, so we go from 1 over delta to 1 over delta d bar. And I think I'm going to stop here, maybe take any questions if there are questions. I'll see if my query is loaded. If my query is loaded, then I'll maybe. Sorry, it hasn't loaded. I'll load up that query before the next one, and I'm going to show you the results of the query. I'm going to show it to you regardless of whether they're good or bad. The point I want to make is that they're going to be bad, but it's possible that something changed and the results are actually going to be very good. The next lecture is going to be on credit networks. So we're going to switch tracks completely from computation and go back once again to thinking of things more from a behavioral point of view.